Okay, I'm not really sure how this is going to go because when I teach this class face-to-face, we do these problems in class, and then I give students some examples to go by and then set them up in groups to go over these. So how should you do this? I'm not really sure because here you have the question. This is just right from the book. What is it? Box problems 1 through 4 in box 3.1. And I'm giving you the answers here. So you know what they're supposed to be. I just double checked these this morning when I was getting ready to record this lecture. So I don't even know if you want to listen to this right away and try it and figure it out on your own. And then I have this graphic here that describes what I had mentioned before about the air quality index if you have an app on your phone and what it all means. So if you want to check your AQI for where you're sitting right now, go ahead and do that. I'm not going to do that today, but you can do that. Okay, so let's see how this goes. And what I have here for you is, and you've had Gen Chem, you've had a bunch of math classes. There's no one recipe for doing every single problem. The thing is, you have to have the right tools and know how to use them. So I tried to make this list of tools here, and these are not steps, like step 1, step 2. These are just the things you need to understand, and then how you put the puzzle together, if you will, or what tool you use to solve the problem is up to you. Another thing that comes in handy is just understanding what you're given. And we're going to see how this goes. So maybe what I'll try to do is talk through the first example in a lot of detail, and then you can stop it and try the rest of them on your own, and then come back and listen to my review of each problem successively if you need them, or listen to what I say after you try it yourself, or after you try it yourself and get frustrated that you can't get the right answer, or you get the right answer and you want to see how I did it, because you may have a better way of doing it. You may have a more efficient way of doing it. And one thing I just want to say before we get started is units and concentration in the atmosphere is in my view, a different mentality than units and concentration in a solution in a lab. Right? Like say you're just dissolving something in water, or you're dissolving something in ethanol. The thing you dissolve is called the solute. The thing you dissolve it in is called the solvent. And the whole thing is called the solution. So in the atmosphere, and I found this really helped me out, is what's the solute when we talk about air quality? The solute is the pollutant. It's the molecule that's causing the pollutant. And we don't really care about the solvent that much because it's basically air and everything in it. The nitrogen, the oxygen, the carbon dioxide, and the pollutant. So we don't really think about solvent. So we think about solute, which is the analog for the atmosphere, would be pollutant, and then the overall solution, which is I'm just going to call air, because air is catch-all for everything, pollutant, non-pollutant. Okay, if you keep that in mind, that might help you, maybe it'll confuse you, maybe it'll be more clear when we go. Okay, so the first one, we're given 32 parts per billion and asked to convert it to 3 other things. Okay, let's go through this. I don't have a ton of notes on this, so let's see. This is problem number 1. I'll try to be a little organized. And I thought about recording separate videos for each problem. That doesn't seem to make any sense. So this video might be long. Just start and stop it whenever you want. Okay, so we've got 32 parts per billion is what we're given. And I tried this one, it looks kind of obvious, but I wasn't sure exactly how to explain it, but I think this is the easiest way to. So 32 parts per billion, and we want to go to parts, what are we asked to do? Go parts per million? Yeah, parts per million. Okay, so parts per billion is picked for a specific purpose because the number 32 is just, that number makes sense. So I think the easiest way to think about this is what's the difference between a billion and a million? Well, 1,000 or 10 to the third. So one part per million is going to be the same thing as 1,000 parts per billion, or if you prefer scientific notation, 1 part per million. That's just The difference between a million and a billion is that. So it doesn't matter which conversion you use there. So you get the same answer. You get 0.032 parts per million. And you may not have written anything down there. It's just the difference between a million and a billion. That's all it is. But also, I just want to point out, that's why you would not pick parts per million for whatever pollutant this is, because it's just a more abstract number. 32 is easier than this, and also this drives to a point. You pick the right unit for whatever it is you're measuring, and also scientists will certainly tell you, sometimes the units picked so it sounds small. Like this sounds like a low concentration. This sounds like a big concentration, even though they're both the same. Okay, so that's A. In part B, what are we doing? You want to go to molecules of pollutant per cubic centimeter of space, of all air. So cubic centimeter of everything. Okay. Well, for this one, what I found helpful is to know what parts per billion means. And sometimes I start out with this one. So what does parts per billion mean? That means you have 32 molecules of pollutant. I almost wish they would have used a specific pollutant for each of these, but that's okay. So whatever the molecule is, for every billion molecules of air. What units are we going to? We want to go to molecules of pollutant per cubic centimeter of air. Well, we're already halfway there. So, molecules of pollutant per cubic centimeter of air. Cool, that's great. So we just leave that alone. That one's fine. The numerator is done. So what we need to do is we need to convert the denominator to cubic centimeters. How on earth do you do that? How on earth do you go from some number of molecules, a complex mixture of air, and how do you go to a volume? Because that's what this is. This is a volume. I think I'm kind of giving it away. There's really only one way to do it. Right here. And actually, we need two things. We need this, and we need this. P equals nRT. We can solve for volume. We have a pressure, don't we? Yeah, the pressure is 1 atmosphere pressure. Do we have the number of moles of air? No, we've got molecules of air, but we can convert that to moles, can't we? That's a constant, 0.08206 liters times atmospheres over Kelvin times mole, and the temperature is 25 degrees Celsius, which is 298 Kelvin. So if you want to stop the video, we're good to go here. We're going to solve for volume. We're going to convert that volume to cubic centimeters, and then do the division. So if you want to stop the video and see if you can do that on your own, that's great. So we need to, okay, so we know that volume equals number of moles of air, which we can convert that, times R times T over P, follow the units. Now I'm going to try to write this here. So moles of air, the molecules divided by Avogadro's number would give you moles. But let me put that in parentheses here. So we have 10 to the 9th molecules. Now it's really important to know that's not molecules of pollutant. That's total molecules in our sample space. Molecules of air, maybe not a great way to put it, but I think it's helpful for me anyway. Divided by 6.022 times 10 to the 23rd molecules of air, molecules of anything actually, per mole of air. And follow units, molecules will cancel, so it'll be moles. So moles are the units you want right there. Times R, 0.08206 liters times atmospheres over Kelvin times moles. Times the temperature, 298 Kelvin, divided by the pressure, 1.0 atmosphere, so we didn't have to do any unit conversion there. And follow your units. Moles will cancel, Kelvin cancels, atmospheres cancel. So we're going to get something, something, something liters. Okay, I came up with the better, right? And sig figs here. I don't think I'm doing sig figs right. I think you want 3 sig figs here. Our final answer will have 2 sig figs. So this is a little sloppy, but I came up with 4.1 times 10 to the minus 14th liters, which is, I'll let you figure this out, 4.1 times 10 to the minus 11th milliliters, which is the same thing as a cubic centimeter. So your last step is to take the molecules of pollutant 32 divided by 4.1 times 10 to the minus 11th, and I came up with 7.8 times 10 to the 11th molecules of pollutant per cubic centimeter of space. And I think that's right. I'm going to check that with what I wrote on here. Okay, I wrote down 7.9 on the slide, so I must have rounded it. That's fine, no problem. And cool, and the last one, I think I can fit this on here, is letter C. So molarity is not a very common unit in the atmosphere, but it kind of ties into what we've done before. Molarity, as you might recall, is moles of solute over liters sol solution, total solution. So here's going to be your moles of pollutant over your volume expressed in liters. Now I think this one we can kind of piece it together because we have the volume. We have the volume of our space already in liters right here. The thing we don't have, and really you should be stopping the video, so we have the volume here, and we can convert this to moles, 32 molecules, we can convert that to moles pretty easily. So if we have 32 molecules of pollutant, kind of running out of space, we're going to divide that by 6.022 times 10 to the 23rd molecules per mole, sorry. The point is it's 32 divided by Avogadro's number. That'll give you the moles divided by the volume, which was 4.1 times 10 to the minus 14th liters. And you end up getting a number that doesn't really help us. In my opinion, I'm not sure why we would do it this way. So I came up with 1.3 times 10 to the minus 9th capital M moles of pollutant per liter of air. Yeah, okay. All right, I'm obviously going to need some time to erase this. So the next one, again, hopefully this helps you, is I'm going to do these a little bit more quickly. So starting with molecules per cubic centimeter, same temperature, same pressure, converted to molarity in part per million. So again, it's picking the right tool from our job here. Now there, looking at the next one, yeah, I'm just going to do one at a time. Because so far, there's no mass in any of these calculations. There's nothing in here with grams or micrograms or anything in these first couple of problems. You run into grams in the last two problems. Now, if you see grams, that's where we're going to need the periodic table. So that was a preview of coming attractions. So for this number 2, just going to have to give you a minute here. I don't have an easy way to do this. So problem 2, we're starting with molecules per cubic centimeter, so kind of going backwards. Yeah, a lot of this is just the reverse. And you just want to get it done. So, start writing it down, trying to figure out what you're doing next while I erase the board. Pretty much sounds like a regular class, doesn't it? Try to leave my puzzle pieces up here. And I might be able to do these a little bit more quickly. Well, I just set it up, and then you do the math, and then come to office hours if this isn't making any sense, because again, I don't know how to do problem solving sessions with the video, because I don't know what questions you're going to have. Okay, so what are we doing now? Number 2. And 6.0 times 10 to the 14th. It's a big number. So that's molecules, again, of pollutant. Oh, another key thing is number 1 and number 2 don't involve a specific pollutant. If they don't involve a specific pollutant, how can you possibly need the periodic table? That's kind of interesting. If it doesn't matter, you don't really care what molecule it is, you don't need to know its molar mass in the periodic table, you don't even need that. That did not dawn on me. And we're still dealing with 1 atmosphere and 298 Kelvin. I wish we would have changed those up, but that's okay. And so the number being 6.0 times 10 to the 14th molecules of pollutant per 1 cubic centimeter of air. So I'm just simply rewriting this, the units, because the units matter. The numerator is pollutant, the bottom, the denominator is the volume of air, in this case measured in cubic centimeters. Okay, so what are we doing in part A? We want to go to molarity, so maybe I'll do it this way. So molarity is moles of pollutant per liter of air. That's what we want, because that's molarity. So those are synonyms. So this is a unit conversion problem. We don't need PV equals nRT. We don't need anything. Well, we need something, but we don't need PV equals nRT. We're already given. Remember, why did we need PV equals nRT before? We needed PV equals nRT before to go from molecules to a volume under a certain set of conditions. We don't need that for this particular problem, I don't think. We will need it for part B. Yeah. Okay, so this is a unit conversion problem. So see, if you want to figure it out, go for it. So you have to convert this to moles, this to liters, and that's it. So 6.0 times 10 to the 14th molecules. I'm not going to write pollutant over and over again. Over 1 cubic centimeter. Now it's understood. Molecules. Okay, I'm going to stop saying that. So let's get the numerator done. So 6.022 times 10 to the 23rd molecules is a mole. So check, the numerator's done. And you probably know that it's 1,000 milliliters in a liter. So the same thing as 1,000 cubic centimeters in 1 liter, or if you want to write 10 to the 3rd, that's fine. Remember, cubic centimeter to milliliter are the same thing. So you just do the unit conversion. Moles per liter, and you get 1.0 times 10 to the minus 6 molarity. Yeah, okay. Parts per million. Parts per million. So remember what parts per million is. It's molecules of pollutant divided by total molecules of air scaled to parts per million. Okay, so what do we need here? Well, we've got our molecules, don't we, of our pollutant. We don't have our molecules of air. Okay, so to go from a volume to molecules, we have to use PV equals nRT and Avogadro's number. So the ideal gas equation will give us moles, no problem. PV over RT, piece of cake. P is 1 atmosphere, T is 298, R is 0.08206. Our volume, guess what, is, our volume is given to us in the original problem. It's this many molecules per 1 cubic centimeter. Well, what's the volume? If it's 1 cubic centimeter, that's the same thing as 0.001 liters, or 10 to the minus third liters. 1, 2, 3. I think that's right. And I don't think I need to sketch this one out, because when I did this, I came up, so just do the math. Pressure's 1, 0.001 liters, just a cubic centimeter converted to liters, no problem. R is R, T is T. I came up with 4.1 times 10 to the minus 5th moles of what? Not pollutant, moles of air. So everything. And then, well, how do you go from moles to molecules? Just multiply by Avogadro's number. I'm not even going to show that. So show the unit conversion. Go from moles to molecules, because that's what this does. And I came up with, what did I come up with? 2.46 times 10 to the 19th molecules of air. Now, this was the part that it's not that hard, but it took me a while to get my head around this. So that's the number of molecules of air. So in my chemist brain, I just want to do molecules pollutant divided by molecules of air, because that makes sense to me. That's just like a good concentration. But that would not give us a number that is easily interpreted. So what we do is, if it's that many molecules, that means it's, are we doing parts per million or billion here? Parts per million. So remember what a million is. A million is 10 to the 6th. So this is the same thing as 2.46 times 10 to the 13th million molecules of air. There may be a better way to think about it than that. So basically, I'm just taking 10 to the 6th out of this. So this is 2.46 times 10 to the 13th million molecules of air. So to get ppm, we take, so to convert this to parts per million, you have 6.0 times 10 to the 14th molecules of pollutant divided by 2.46 times 10 to the 13th million molecules of air. Again, there may be a better way to do this. I have a solutions manual in the book, and maybe they do it differently too. But I came up with 24, because that's the answer. Parts per million. Because you scale it for per million molecules of air. Okay, So 24 ppm, I think that's right. Nice, okay. That's problem number 2. Problem number 3, I'm looking at my watch because I want to make sure that the parking meter doesn't run out. And the next one, part A is pretty straightforward, and the second part, we actually have to calculate a mass because it's ozone. So if you actually see a chemical formula, that indicates that you're going to have to go to the periodic table. So if you want to get all your data together, the only other piece of the puzzle you're going to need is the molar mass of ozone, which is oxygen times 3, 47.997 is what I came up with. But let's go through this one. And you already have the answer, so if you don't want it, that's great. And hopefully as you go on with these, I think I put a few on the homework. And I can always make up more of these. Also, I'm hoping that you understand that, sure, you could just say this problem into your AI chatbot, it'll spit out an answer to you. But yeah, okay, that's a great way of getting an answer. And if you're in the workplace and all you do is care about making the conversion, you don't care about what it means, you're not there yet. I think it's important to understand these units because they make you understand the difference between what it is you're measuring. Is it the pollutant? Is it the total air? When do you have to use the periodic table? You don't want to just use a conversion table or hit a button and it just gives you the answer. Okay, so this is problem 3. Let's jump right into it. 40 parts per billion. What does that mean? So that means there are 40 molecules of ozone for every 10 to the 9th molecules of air. That's what it means. And I can probably just sketch this out. So the first one, we're trying to go to molecules per cubic centimeter. So somewhere down here, we want to get molecules of ozone per, what are we trying to get, cubic centimeter? Cubic centimeter. So we've seen a problem like this. This is done. All we have to do is take this. Haven't we done this already? Take molecules of air, convert it to a volume. We've done this already. Yeah, okay. Well, sort of. So we need to convert this to volume in cubic centimeters. So that's P equals nRT. Volume equals nRT over P. I don't think I'm going to set this one up too much. I'm just going to talk through it. You're given the pressure, 0.95. You're given a temperature, which is 300 Kelvin. R is R. N is the number of moles. Where do you get moles of air? Well, you just take this and divide by Avogadro's number. Okay. Well, when I did the math, I came up with 4.3 times 10 to the minus 14th liters. And I think you can finish this off. So convert that to cubic centimeters like we did before, and I came up with what's already there. 9.3, is it the same? Yeah. That sketch should be enough for you without having to watch me write a bunch of data up here. And B is our first time we're introducing mass. Mass is used a lot for particulate matter, for PM 2.5. And we're trying to get micrograms of ozone per cubic meter. And there's nothing that says we have to start from the beginning. In fact, when I did this problem, I started from here. Well, I've got molecules. I should be able to go from cubic centimeters to cubic meters. I should be able to do that. Convert cubic centimeters to cubic meters. That should be okay. And molecules to micro, I should be able to do that too. This is a unit conversion problem. I guess everything is a unit conversion problem unless you use PV equals nRT. So this is how I did it. 9.3 times 10 to the 11th molecules of ozone for every 1 cubic centimeter. Doesn't matter which one you do first. Let's do, so I know it's, what is it, 100 centimeters is a meter. Or you can do 1 centimeter is 10 to the negative second meter, it doesn't matter. But then I gotta cube that. So you have to have 100 cubed, or this would be 10 to the second raised to the third. So it's gonna be 10 to the 6th cubic centimeters is 1 cubic meter. Good to know. Oh, that's on you, not me. And molecules to grams, micrograms, I should be able to do that. Okay, let me sketch this out. So 6.022 times 10 to the 23rd molecules is a mole. And I don't think we've done this yet. A mole of ozone is the periodic table, oxygen times 3. I came up with 47.997 grams. A little sloppy, but I think you can follow this. And then micro. So 1 microgram is 10 to the -6th grams. Always double check. So cubic centimeters cancels, leaving us with cubic meters. We want that. Molecules to moles, moles to grams, grams to micrograms. I think we're good to go. And you should get the answer, 74.1. Okay, I have 74.2. Depends on how you math, but that should be right. So that's kind of a unit conversion problem. And the last one is kind of this one in reverse, sort of. Yeah, okay. Let's do the last one. And we have a different temperature and a slightly higher than regular normal atmospheric pressure, which is fine. So our temperature is what, 290 Kelvin. And then pressure is 1.04 atmospheres. So let's just start off with what we're given and figure out what makes the most sense to do first. So we have 1,000 micrograms of carbon monoxide, so we're going to need the molar mass. It's about 28.01 carbon plus oxygen per cubic meter of air. Cubic meter is a pretty typical volume when you're talking about, especially indoor air quality. It's often measured in especially airflow is often cubic meters per second, and how airflow works in an industrial setting. And then okay, I forget what we're doing. And we want to go to parts per million. Okay. So remember what parts per million is. It's molecules divided by molecules. actually 10 to the 9th molecules. So is it, sorry, keep moving back here. Yeah, parts per, yeah, million. So 10 to the 6th. So millions of molecules. Okay, so we want to convert 1,000 micrograms into molecules. How do you do that? That's stoichiometry. So you take micrograms, convert it to grams, convert it to moles, multiply by Avogadro's number. The bottom part, you want to take a volume, cubic meters, and convert that into millions of molecules. I think. Millions of molecules. So how do you go from a volume to molecules? Well, that's where you use the ideal gas law. That looks like it's 6. IGL, ideal gas law. So we have to use 2 different procedures here, but it's the same basic idea. So let's just set this up and crank through it. So we have 1,000, so let's do the numerator first, then the denominator. So 1,000 micrograms, you should be able to do this. And it's carbon monoxide. A microgram is 10 to the minus 6 grams. We know it's 28.01 grams is 1 mole, and this is all carbon monoxide. And then we know that a mole is 6.022 times 10 to the 23rd molecules. Great, do that math, and I came up with 2.15 times 10 to the 19th molecules. So those are the parts in the numerator, molecules of carbon monoxide. So P equals nRT, and we want to get moles. But then we're going to take the moles and multiply by Avogadro's number, and then divide that by 10 to the 6th, so it's millions of molecules. So go ahead and do that if you think you know what you're doing. We just have to make sure we put the units in right. The only unit that we don't have is volume. That has to be liters. So we have to convert a cubic meter into liters. I should know this, I didn't know this. A cubic meter, so a box that's a meter on each side, is 1,000 liters. I don't know if you knew that, but I didn't know that off the top of my head. So I just did the unit conversion. So 1 cubic meter, so a meter is 100 centimeters. We did that before, raised to the 3rd power, so it's 10 to the 6th. Cubic centimeters is a cubic meter. And then you know that it's 10 to the 3rd, 1,000 cubic centimeters, 1,000 milliliters is 1 liter. So again, this could be, if you want to do the math easier, this is going to be 10 to the 6th divided by 10 to the 3rd. 10 to the 6th divided by 10 to the 3rd is 10 to the 3rd. So it's 1 times 10 to the 3rd liters. Don't mean to insult your intelligence if you're better at unit conversion than I am. So it's 1,000 liters. Now we're good. Put in your pressure, put in 1,000 liters, put in R, put in your temperature in Kelvin, multiply by, get that number or not, then you're going to multiply whatever you get there times 6.022 times 10 to the 23rd. Okay, then I will give you this part. Is I came up with my final answer after all that work is 2.63 times 10 to the 25th molecules of air, which when you divide that by 10 to the minus, or 10 to the 6th, excuse me, a million, 10 to the 6th, you get 2.63 times 10 to the 19th million molecules of air. Finish it off. Molecules of pollutant, carbon monoxide, divided by millions of molecules of air, and you end up getting 0.82 ppm. ppm. That is a good problem. I really like that problem. It combines everything. Greek prefixes, unit conversion, grams, moles, PV equals nRT, and Avogadro's number. That's a problem to start. That's a good one. That requires everything. And I think the last one, one's pretty easy. What are we trying to get? So this is B. We're trying to get molecules per cubic centimeter. So molecules of carbon monoxide per cubic centimeter. Where does it make sense to start? I think it makes sense to start with the original number. I don't think it makes sense to start with ppm. Maybe it does. Maybe you have a better way. I think it makes sense to start here, because we can convert this to molecules pretty easily. In fact, we already did that, didn't we? We have that number. Yeah, don't we already have most of this work done? Molecules per cubic centimeter? Yeah, so we already did this part. We already have the molecules, so we already have the fact that it's 2.15 times 10 to the 19th molecules of carbon monoxide, and that's in the original number, is a cubic meter. Is that it? That's all we have to do? Okay, yeah, all right, let's not make this harder than we need to. A meter is 100 centimeters in the denominator. We have to cube it. So we have to take this number divided by 10 to the 6th. Well, that's not too bad. That's 2.15 times 10 to the 13th. Yeah. Okay, well, you can see the units. All right, so that was long. That was 4 problems. But those are the kinds of things you want to be able to do. Those are representative. So crank on the homework, get together with classmates, work these problems out, and then we'll just have to deal with it during office hours or synchronous instruction.